Hello, everyone. Welcome to our webinar today. Our company is Statistics Solutions. We assist with dissertation consulting. During today's webinar, we are going to discuss a breakdown of regression models. So I will give a definition of each type of regression, and then we'll look at some examples in how to analyze these specific regressions. My name is Justin D'Souza. I'm a quantitative specialist here at the company. We're going to send everyone a copy of the recording as well as a copy of the webinar. If you have any questions, you can type them into the chat box or you can use the Q&A box. And at the end of the session today, I will be doing a Q&A session. All right, so let's go ahead and dive in. First, I'll give a brief overview of what we provide as Statistics Solutions, our company. Then we will look at the different types of regression models, and I'll give a demonstration in our company-developed software, Intellect the Statistics. Then we will conclude with a summary and a Q&A session. Our company, Statistics Solutions, helps with virtually every part of the dissertation journey. We have literature review specialists, and we have methodologists, both quantitative and qualitative. So starting with topic development and going all the way to the final defense and journal publications, we can help edit your dissertation or your thesis. We can help you frame research questions, identify a theoretical framework, identify a purpose or a problem statement, figure out what is the best methodology to support your study, if it's quantitative, qualitative, potentially mixed methods, and help figure out, the best survey instruments that you could use. It's best not to develop your own tool, so we can help you find a survey that already exists. We help with IRB forms, data entry templates. We can assist with identifying the best analysis to address your research questions. We also have a SurveyMonkey account on file. If you need help uploading a survey, you can sign on with us and we can upload the survey for you. And then with the final few chapters, the results chapter, quantitative and qualitative, if you just send us your data and your template, we can crunch the numbers for you and we can provide it into an APA write-up. Then we assist with the discussion chapter, which is wrapping up, the findings, connecting your findings to previous literature. And we assist with PowerPoints for proposal and final defenses, and we can help condense your dissertation into a journal publication. If you have any questions about the services we provide, you can give us a call for a free consultation at 727-442-4290. We're looking at linear, logistic, and ordinal logistic regressions today. So before we kind of identify those, it's important to lay the foundation for what is a level of measurement. The type of variables you have is going to determine what is the best regression model that you should use. In general, there are three different types of measurements. We have continuous, nominal, and ordinal measurements. A continuous variable is one that falls on a continuum or an interval. Examples of these include test scores, temperature, height, weight, GPA, composite scores from a previously validated survey instrument. If you're using a Likert scale survey, there are references and citations that say when you take an average of those Likert scale items or a sum, that resulting variable is continuous. Then we have nominal variables, which are categorical factors. There's no intrinsic order to a nominal variable. There's no hierarchy. Things like gender, ethnicity, passing and failing of an exam, course, or field in an industry, those are all nominal. Ordinal is a subset of a nominal variable. It's categorical, but there is a natural progression or a natural ranking to that variable. Something like education level goes up a ladder. A single item on an ordinal scale is an ordinal item, strongly agree to strongly disagree, something like that. So once you've understood these definitions, and assuming you have your research questions kind of set in stone, then you can run a linear logistic regression potentially. Regressions are used when you're trying to examine the predictive relationship between a variable or a series of variables on a dependent factor. So the terminology is usually an independent variable or variables are your predictors, and your outcome or your dependent variable is a criterion variable. When you're doing a linear regression, the outcome is always going to be continuous. So your dependent variable is going to be a continuous interval ratio type of variable. When you go into the logistic regression family, that's where you have more categorical outcomes. Something like a binary logistic regression implies that your outcome only has two possibilities. That's where the word binary comes from. If you had passing and failing as your outcome, then you can do a binary logistic regression. If you have something with more than two categories, then you do a multinomial logistic regression. So if you're trying to predict ethnicity or race or occupation, that would be a categorical factor with probably more than two possibilities. So you can do a multinomial logistic regression. An ordinal logistic regression is used when your outcome is an ordinal measurement. Okay, something like education level or a singular Likert scale item. That would be an ordinal criterion or dependent variable. I'm using criterion, dependent, and outcome kind of synonymously here. They all apply. So the type of regression you use is dependent on how your outcome is measured. Okay, continuous, you do a linear regression. Nominal, you're doing a binary or multinomial logistic regression. Ordinal, and you go to an ordinal logistic regression. Okay, as far as the predictors, your independent variables, these can really be any level of measurement. You can have continuous predictors, you can have nominal predictors, you can have ordinal predictors. However, the coding, when you use a software like SPSS or R or Stata, the coding for predictors is very particular. For a continuous variable, you don't need to make any adjustments. You just put in a continuous factor like GPA or height, BMI. You put that as it is. You don't make any adjustments. So that's fairly easy. If you have a dichotomous predictor or a binary predictor, such as passing and failing, then you need to code. You're going to have two possibilities, and usually the absence of a condition is coded 0, and the presence of the condition is coded 1. So you would code passing and failing 0 as a fail, 1 as a pass most of the time. And then if you have a categorical factor with 3 or more possibilities, this is where you have to look at dummy coding. So there's a lot of research on this, a lot of explanations on YouTube that you can look at that describe dummy coding. So the idea behind this is that, if you put in ethnicity into a regression model, the regression model is not going to know what white, Black, Asian, Hispanic, other. It doesn't understand those different categories. So it's up to us, the researcher, to assign meaning to those categories. And the way that's done is by assigning a reference. So in this example here, we have race. You have to pick one of these categories to be your reference category, to be your reference group. So every other possibility, every other category is compared to that reference. When I look at ethnicity or race, most of the time, the white ethnicity is treated as the most prevalent, or it has the highest frequency in most samples. So then you treat that as the reference. So essentially what you're doing is you're creating, from these 5 possibilities of ethnicity, you're creating 4 independent variables from it. Those are called dummy coded variables. So you have black versus white, and Asian versus white, then Hispanic versus white, and then other versus white. So black would be coded as a 1, white would be coded as a 0, Asian would be coded as a 1, white would be coded as a 0, and so forth. SPSS can do that automatically. Our software, Intellectus, can also do that automatically, but sometimes you need to develop that manually. You have to manually create the dummy coded variables. I prefer to do it manually because I don't trust softwares always to do that process right. So yeah, check out some YouTube videos on dummy coding. It sounds complicated, but it's not really difficult to set up. Okay, and then as far as the process for interpretation, the first thing you want to do before you even get to this is you need to have research questions. You need to have research questions and hypotheses. You need to know exactly what predictors you're looking at and what is your dependent variable. And then once you've done that, and assuming you have your data collected, then you need to verify that the statistical assumptions are supported. So almost every inferential analysis has statistical assumptions that you need to verify. So I have a pretty good reference here. I'll put it in the chat box. But if you go to statistics layered, you just type that into Google and you just type regression, be specific and say linear regression. And you go to this hyperlink. Statistics layered provides demonstrations in SPSS how to do things, but they also give a list. I see a lot of universities referencing this website now. You can see it lists all the assumptions that you should check before running linear regression. So it goes through a bullet point list explaining, what looks good for this assumption to be supported, what is not so ideal. We have things like linearity, we have no significant outliers, we have independence of observations, homoscedasticity. There's quite a few. Normality is an important one as well. Depending on what reference you read, you might not see so many assumptions. I think 7 assumptions is on the high end for a linear regression. I've seen between 3 and 5 usually. It really depends on what reference you are supporting. And you'll just be consistent. If you report this in your methodology and you use that particular reference, then check the same assumptions in your results chapter. Okay, let me put this in the chat box just for reference. And there we go. Oh, I didn't put that in the right box. Here we go. There it is. Okay. All right, so once you've checked for the assumptions, then it's something to keep in mind is that linear regressions have more stringent assumptions compared to a logistic regression, because linear regressions are considered more of a parametric analysis, whereas logistic falls into the non-parametric family sometimes. So you have to check for things like normality. That's a really important one that you can't check for a dichotomous or binary outcome. Okay, and then I just listed a few of the most popular or frequent assumptions to check: normality, homoscedasticity, absence of multicollinearity. I think those are the most important. Then we'll go into Intellectus in just a minute here. I'll show an example of how to run a couple of regressions. But the process is fairly uniform across every regression model. First, you need to look at the Omnibus test, which identifies, do you have a collective model fit? What is the predictive strength of your regression model? And usually that is identified with an Ftest for a linear regression or a chi-square test for a logistic regression. And significance, almost uniformly through statistics, is identified with a p-value being less than 0.05. So if your p-value is lower than 0.05, then you have a collective significant model. Then you interpret the coefficient of determination. That is an R-squared value or a McFadden's R-squared value. And that's telling you how much variance or change in your dependent variable can be explained by your predictors. And then step 3 is contingent. It's reliant on step 1 being significant. So if you don't have a significant model, then you don't go to step 3. But if you do have a significant collective model, you go to step 3, and that process is then interpreting each predictor in the model. How significant is each independent variable in predicting your dependent variable? Okay, I know that's kind of a lot to explain verbally. I think it's easier to explain it visually by looking at an example. Okay, so this is our company software. It's called Intellectus. I do see some familiar names in here, so I'm sure some of you have seen this before, but for those who are not familiar, you can upload a data set into Intellectus. So you can upload a CSV, Excel file, SPSS, SAS, or Stata. Very much like SPSS and how it's organized and how the data set is organized. So I've uploaded a sample data set here, which contains different car models, Mazda, Mercury, Toyota, and so forth. And we have rows as individual car models, and we have columns as variables of interest, miles per gallon, how many cylinders, horsepower, weight, so forth. You can see within Intellectus, you can clean the data. You can recode variables to categorical or nominal or ordinal. You can identify outliers. You can replace missing data with imputation. You have a Likert scale survey. Many Likert scale surveys require, I shouldn't say many, some surveys require reverse coding, which is just flipping your Likert scale. So you can do that function here. We have a variable calculator, which can be used to compute composite scores. You can transform data into different distributions, square root, squared, cubic root, cubic, and you can even download the data. So once you've made adjustments in here, you can download it directly into Excel format. We also have plots, which you can look at the relationship of your variables visually. So for example, here, if you do a scatter plot between mileage and say horsepower, it's going to give you a scatter plot, at which point you can edit, the labels, you can take out the title, you can change the X and Y axis, you can change the color. Right now it's blue. APA says most things should be grayscale, so you can change it to gray like that. And then you can export into a JPEG, a PNG, or you can download it as a Word file, okay? Then we also have a decision tree here, which will, if you're at the methodology phase or fairly early on, you can use the decision tree here to figure out what is the best analysis to run to address the research question. So, today we're looking at predicting an outcome, which is the regression family. So say you want to predict an outcome and the outcome is going to be scale, or that means continuous, then it's going to tell you, hey, a linear regression is probably the best option here. You also have data analysis plans, which for a linear regression, for example, this is what would go in your methodology chapter. We give you a sample research question along with hypotheses. We give you a definition of what a regression is, what assumptions are going to be checked along with references, and what is the process for interpretation of that regression model. And we have references at the bottom. There are also power analyses, okay? So power analyses are used to figure out what is the minimum sample size ideally to run a particular analysis. So if you're doing a linear regression, We give 3 different write-ups here. And, depending on what effect size you're going with, what the strength of the relationship you are anticipating is, it's going to give you a minimum sample size target. So a large effect size, we need 25 participants or 25 rows of data, medium effect size 55, small effect size 395. And then we have the actual analysis. Okay, so these are the analyses that we have within Intellectus, starting with fairly simplistic things like descriptives. So if you wanted to look at descriptive statistics on the variables of interest, then you can just select that option and check mark what you want to look at descriptives on. And depending on the level of measurement on this one, going to give you either a frequency table, so something like transmission type of a car, automatic or manual, that is nominal or that's categorical. So it's going to give you frequencies. We have 19 cars that are automatic. Those 19 cars represent 59% of the sample. It gives you an interpretation for the most prevalent category. And then for anything that is numeric or continuous, it's going to give you mean, standard deviation, the sample size, the minimum, and the maximum. Okay, so for mileage, the car with the lowest mileage had 10.4 miles per gallon. The highest was 33.9. The average was 20 miles per gallon, approximately. Then, we have a bunch of other tests. I do other webinars that go through correlations and ANOVAs. Today, we're focusing on regressions. We also do have some more advanced analyses like mediation, moderation, HLM. We also have path models if you're doing structural equation modeling or CFAs. But today, we're focusing on regression, okay? And let's say that our sample research question is, what is the relationship between, similar to the scatter plot I did here, between mileage and horsepower? So that's where you go to a linear regression. Our dependent variable, or the outcome, will be horsepower. And our independent variable is going to be mileage. If you go to options at the top right here, you can see all the different things that will be presented. We're checking for normality. We're checking for homoscedasticity. Those are the 2 essentials for this. Then we click calculate. And it's going to present an APA interpretation along with graphs and charts. Okay, so the first thing it does is it checks for normality with a QQ plot. And this looks fairly good. For normality, you want your data to closely follow this diagonal trend line. It looks fairly good, some slight deviations. If you hover your mouse over the figures, you can see the different possibilities. So the top left quadrant here is kind of what we're aiming for. Then we have homoscedasticity, which is looking for random scatter and random spread. And that's what we have. We don't see a recurring pattern in this, so that's ideal. Multicollinearity, I'll show that in the next example. You can only check for absence of multicollinearity if you have more than 2 predictors. 2 or more predictors. We only have mileage in this one, so it doesn't verify it. And then you get down to the linear regression. Okay, so let's look back at the PowerPoint. First thing you need to do is interpret the Omnibus test. And that is done with the Ftest. Okay, and that is one of the first things presented. The results of the linear regression were statistically significant. Here's the Ftest, and it is significant. Okay, this is below 0.05 on the p-value. Also presented in the note at the bottom here. Collectively, we have a significant regression model. Then you interpret the R-squared value. That's step 2. So the R-squared is also interpreted right here. Excuse me, right here, 60.24%. It's in the bottom in the note as well, 60%. It's a decimal, but if you move it over the decimal over right twice, that's about 60%. What it tells us in this example is that about 60.24% of the variance or the change in horsepower is explainable by mileage. Then the third step, remember, is contingent on step 1 being significant. We do have a significant model, so we do jump to step 3 in this example, which is looking at each predictor on its own. This is where you dive inside of the table and you go across the mileage row right here. And you look for significance. First of all, is the p-value significant? Which is in the final column here. It is. This is below 0.05, meaning that mileage does have a significant predictive effect or relationship on horsepower. Then you look at the unstandardized beta coefficient, which is right here. It's at italicized B. And you look at two things. You look at the directionality. Is this a positive or a negative value? In this case, it's negative. And you look at the actual value. So what we can say here is that as mileage increases by 1 unit for every 1 mile per gallon increase, horsepower decreases by 8.83 units. So we have an inverse relationship. As mileage increases, horsepower tends to decrease. And that's kind of what we see here in this scatter plot that I did fairly early on. You can see there is a negative trend. As mileage increases, horsepower tends to be decreasing, which intuitively that makes sense. We can also do an example of a binary logistic regression. And to do that, remember, you need to have, going back to the PowerPoint, do a binary logistic regression, you need to have a binary outcome, something that is dichotomous. And I believe we do. Okay, something like this, transmission type, just automatic or manual. So we could say, you know, how does mileage predict what transmission type a car has? And you would just do a hierarchical, I'm sorry, not hierarchical, you do a binary logistic regression. Binary means 2. Our outcome has 2 possibilities. Dependent variable will be transmission type, that. And then the independent variable, select mileage again, just keep it simple. Okay, for this, you can see that no assumptions are presented. Whereas for the linear regression up here, we looked at normality, we looked at homoscedasticity, potentially multicollinearity as well. But for a logistic regression, there are no strict assumptions, besides multicollinearity, I would say. Okay, what we can see here, we follow the same approach. We look at the collective effect first, then the R² value. Collective effect is down here in the note, as is the McFadden's R². It's interpreted up here. The p-value for the Omnibus test is significant, indicating that mileage does have a significant relationship collectively on transmission type. Then we look at the McFadden's R², which is 0.31. This can be interpreted in the same way, you know, about 31% of the variance or change in transmission type can be explained by mileage. Then you go inside the table and you go across the row for mileage. You don't do this step if you don't have a collective model fit. You kind of just stop there. But we do have a significant model. Therefore, we go inside the table and we look at mileage. And we can see that we have a significant p-value. And then you don't interpret the beta for this one, you interpret the odds ratio. So the odds ratio is telling you what are the odds of a car being manual. And that is interpreted right here. So with every 1 unit increase in mileage, the odds of a car being a manual transmission increase by about 36%. Okay. Higher mileage leads to higher odds or likelihood of a car being manual for transmission. All right, so those are a couple examples in Intellectus. You can also download the document right here at the bottom right once you've run everything you want to run. And it's going to give you a Microsoft Word write-up. And this is what it looks like, very similar to what's on the web page, but this is where you can make edits. You know, you can add your introduction, you can follow the school's template. And at the very bottom here, we have a glossary of terms. We have references for things that were used, and also a glossary of all the terms that were used in the chapter, in case you need a little background on what a term means. All right, so that pretty much covers our webinar today. So in general, if you're trying to predict an outcome, a regression is your best option. You need to have independent and dependent variables to do a regression model. If you don't have independent and dependence, then you can probably just do a correlation, Pearson correlation or a Spearman correlation. Figure out what is the best regression method based on what your outcome is. Then check for the statistical assumptions. There are many references online. I put one in the chat box for statistics layered. Follow the 3 steps for interpretation, Omnibus test, R squared, and then the individual strength of the predictor. Then you can use Intellectus statistics to analyze your data and present the interpretation, or you can use SPSS or Stata. But as you can see, Intellectus statistics is fairly efficient and it's cost efficient as well. Okay. All right, so if you have any questions, you can type them into the chat box or you can type them into the Q&A box. We're going to send everyone a copy of today's webinar, as well as the PowerPoint. If you have any questions about the services, you can give us a call at 727-442-4290, or you can email us at info@statisticsolutions.com. Do we have any questions? Okay, see, we have a question from Suni. Can we do ROC curves with the software? I'm not sure, actually. Don't think so. Actually not something I'm too familiar with, ROC curves. That might fall under a specific analysis approach. Let me just do a quick Google on that. I'm not sure what analysis that goes with. I don't think we have that in here, but that'll be a recommendation that I provide to the software team. Yeah, I don't see ROC curves in here. Do we have any other questions? You can raise your hand as well, and I can unmute you. The audio might not be great with so many participants, but we can give it a try. Hey, Carrie Ann, yes, we will send a copy of the webinar to you. Any questions about regression models, the software, or the services we provide? All right. Well, thanks everyone for joining. Come join us for the future webinars we're doing. I think we have a few more lined up for December. And just let us know if you have any questions. All right. Have a great evening.